Hello everyone. Today I will be talking about safety and performance in programming languages, and perhaps it's worth mentioning that initially the title I was considering was safety versus performance. However, I decided that the word "and" better conveys the premise of this talk. So let's define a few things first. What do I mean by safety in a programming language? I mean the property of having well-defined behavior for valid and invalid programs, and the former is an easy target to achieve because most programming languages are very good at describing what happens to programs that play by the rules. The question and the distinction comes from programs that violate the rules. For example, a program that might read an initialized variable, or a program that might access an array element using an index that is out of bounds for that array, or a program that tries to use an object that is dead. Those programs typically violate the rules of the language, and so we can distinguish languages between those that offer well-defined behavior in those cases that we would call safe, and those that don't for certain reasons that we would call unsafe. Performance, on the other hand, or perhaps efficiency, is the ability to achieve a computational goal when writing a program in that language without unnecessary use of resources, whether they are CPU or memory, network, files, and so on. So a programming language, this is a disclaimer, the programming language can be safe or unsafe in some aspects. This is a fairly uncontroversial distinction, but a programming language technically cannot be fast or slow. It cannot be classified as efficient or inefficient because programming languages are mathematical constructs, and it is not meaningful to talk about the performance characteristics of mathematical constructs. It is meaningful to talk about the performance characteristics of specific implementations and that run on real systems. But programming languages have semantics, and those semantics dictate a lot about how they can or cannot be implemented. For example, if you take C++, it's a language that offers the programmer an explicit way of deleting an object and therefore reclaiming memory for the program. And this means that an implementation of C++ does not need to have a garbage collector at runtime. And indeed, most implementations of C++ do not have a garbage collector available. Some do. And they're perfectly valid, and there are good reasons for them to have it, but it's not required by the semantics of the language. But if you take a language like C# or Java, they do not offer an explicit way of deleting objects, therefore reclaiming memory for the system. So if you were to implement a language like that, to create a new implementation, you would have to ask yourself, how does my implementation ensure that, how do we reclaim memory for the program? And one trivial answer could be, we don't. Since there are no delete statements in the language, then we don't reclaim memory ever. But that would make for a fairly useless implementation, because most programs will fail if they will not be able to be implemented in a language in an environment that cannot reclaim memory. So a more reasonable approach would be to have a garbage collector, which is a memory allocator that does reclaim memory. Only it does so, by keeping track of objects that need to be alive and objects that can go away, and releases them at its own convenience. So even if the specification of the language does not explicitly call out for a garbage collector, and by the way, some do, but even if they don't, their semantics might more or less imply a garbage collector anyway. So we have certain semantics that might favor certain implementation strategies, and certain implementation strategies may favor certain internal data structures. For example, garbage collectors have certain kinds of data structures for bookkeeping associated with them. If you have a reference counting scheme, then you would have you would have other data structures. Namely, you need to at least keep track of the reference count of the object, or if you have object-oriented style polymorphisms, you would probably have something like vtables or something equivalent to keep track of the real implementations or the overrides of your objects. So we have certain data structures implied by implementation strategies, and data structures generally have certain algorithms that are more optimal to operate on them, and so on. So most implementations anyway follow the obvious path, and they improve upon it. So for example, if you are implementing a JVM, you might have a Java bytecode interpreter, and you might improve upon that later by having a JIT compiler that identifies all the paths in the program and translates those to machine code, thereby improving the performance of the program that way. Or you can have a garbage collector that has different profiles depending on whether you're running in a desktop app or a server app, which has different allocation patterns. So there is a causal link between semantics and the performance characteristics of an implementation of a programming language. Now, the common wisdom is that safety and performance are opposing goals, and this is kind of seemingly supported by examples by observing mainstream programming languages. For example, we tend to see languages in two camps, like the high-performance languages like C and C++, which are notoriously unsafe, and they have their own unique classes of bugs that lead to data corruption or security vulnerabilities and so on. But you still could reach for those languages if you want to take full advantage of the hardware, or if you are targeting a resource-constrained device and so on. And on the other hand, you would have safer languages, depending on your definition, that might include Python or Java or Haskell and so on. But these languages are often perceived as slow or bulky, and you would not use them unless you did not care to get the full performance of your computer and so on. This dichotomy is also supported by our intuition. Our intuition tells us that safety requires checks, and checks are an extra thing you need to perform at runtime, so they degrade the performance of the running program. However, this is all a myth, because we are missing one important piece of the puzzle, and that piece I've chosen to call here proofs of soundness, meaning that we, instead of discarding the information that we have about our program at development time, we use that information to prove that a particular operation is safe. Either it's safe all the time, or it's safe for a given input, whether it's user input or input that originates from another part of the program. But we use that information to prove that the particular operation is safe, and then we don't need to check at runtime that it's safe. So and we may also use that information gained from the proof to perform the action in the most efficient way possible to perform that operation. So that is a very useful principle, but as we will discover, most programming languages will happily cut corners on soundness. So the first example of proofs of soundness, and my favorite, is type proofs. They're fairly easy. A language can use type proofs to basically permit programs that are sound from a type theory perspective and reject ones that are not. For example, if you have values like 0, 1, 2, 3, 4, 5, those belong in a set called int, and you could then specify, you can write a function that says I can operate on values that belong to the set of int, and the programming language could then check all the call spots to that function and say, well, if the argument passed to that function has been proven to be to originate from the set of int, then I will allow the call. Otherwise, I will reject the call. For example, if the value being passed belongs to the set of string instead. This is called static typing, and there are obviously statically typed languages and non-statically typed languages. I will not dwell on this slide, but it's worth exploring how the presence or the absence of type proofs affects simple operations like function calls. Because function calls are the bread and butter of a program, every program, and so we better get them right, and we better get them to be efficient. And if we explore how we do it without type proofs, meaning in non-statically typed languages, we have to handle the scenario of what happens when we call a function on objects that are not applicable. And so what happens is we have to choose between safety or performance because we don't have type proofs. Most interpreted languages, for example, choose safety over performance. So what we do is we have this convoluted ceremony where you take the object on which the function is called, if we assume an object-oriented language, or we take its class, depending, in some languages every object belongs to a class cleanly. In other languages, an object might, essentially have its own unique type. But anyway, we take the object or its class, we get a collection of the members, we look up the desired function, which is an expensive operation, whether you do it linearly or you do it with a binary search or you do it with a hash table lookup. It's a very expensive operation for a function call. Then we might check the number of arguments and see if it matches the number of arguments at the call spot. We retrieve the function handle at runtime, we push the arguments on the interpreter's registers or stack or whatever it has. We feed the function handle to the execution engine, whatever that means. If it's an interpreter, it means tell the interpreter to go interpret that function and so on. We keep executing and then we retrieve the value from the return value from predefined place. And this is very slow because it involves a huge number of steps if you think about it. And these data structures that we'll be dealing with, like the collection of members and so on, these are not friendly to the CPU or the cache, depending on whether we're optimizing for speed or for space. We are always making a trade-off. But at least it has well-defined behavior. If the function does not exist, or if it has mismatching signature, usually it's an error that we can handle. But if you choose performance over safety, well, you still lack type proofs, then you can get away with a minimal ceremony, like pushing the arguments of a function to the registers and or to the stack, depending on the calling convention we're using for that particular function, and then we jump to the address of that function, meaning we set the, like in assembly, for example, we set the function, the program counter to the address of that function. We keep executing and then we pick up the return value from, again, whatever place the calling convention dictates. And it's fast because it's short and it's predictable, and predictability plays a huge role in achieving performance. However, anything can happen if the function does not exist or there's a mismatch between the signature and the call, because now without the check you will be basically reading arguments as something other than what they are. You could be reading random locations from memory and things like that, interpreting things as of another type than they are. Very bad things that can happen. But when we do have type proofs, like you do in most statically typed languages, not most, basically all of them by definition, you still get the minimal, fast, predictable ceremony, and you get to access to optimizations like inlining, like I know this is a function that I'm calling, so I might as well bring the body of that function at the call spot and do away with even the ceremony itself. Or you can do tail call elimination, which means in a recursive function essentially reuse the stack frame, the same stack frame as we dive deeper. And it's as safe as you can get because the function is guaranteed to exist and it's guaranteed to match its arguments. Now, type proofs in a language may be unsound, which means that a language might have something that considers a proof, but that proof can actually lead to incorrect assumptions. For example, one such thing is the mutable array covariance feature in JVM and the .NET runtime, which in English would be described as if string is a kind of object, then a string array is a kind of object array. This feature allows reuse of certain functions that operate on object arrays, like reverse sort functions that do not care about the structure of the elements, but they basically manipulate their positions in the array. And you can reuse them without making a copy of the initial array from object array to string array and so on. These were added before generics were introduced in those languages, but this rule is unsound from a type theory perspective, because if you take, for example, an array of goldfish and you store a reference to that array in a variable of type animal array, then it looks innocent, but then later on you try to set the first element of the animal array to be a new tiger, a reference to a tiger, and now what you have done is you've put a tiger in an array that was actually a goldfish array. And now you have all the type and safety of putting a tiger in a goldfish variable, because that's when an array is just a contiguous string of variables. So to be safe, we now have to perform a runtime type check every time we write to an array. Otherwise, to an array at least that is susceptible to that, to an array of a base class, for example. Otherwise, we risk undefined behavior. And there's a quote from Eric Lippert, who used to work on the C# compiler. It says language designers who give up a little type safety for a little performance will discover they have neither. And this is kind of the premise of this talk as well, if you think about it. So another type of proof is Sentinel Proofs. Sentinels are in-band values that carry out-of-band semantics, meaning they are values that carry special meanings, but they're indistinguishable from other values of the type. These are additional values that need to be handled specially, but because they're in-band values, the compiler usually does not enforce their special handling. Perhaps the most famous Sentinel value is the null pointer or the null reference, which is, for example, if you have a pointer type, the valid values of pointer types are numbers that represent the location of an object in a given address space. This is the in-band semantics, but the zero-like null value, which doesn't have to be zero, but for the scope of this conversation doesn't matter, it does not represent an object at address 0. That would be in-band semantics. Rather, it represents the absence of an object. This is what makes it an out-of-band semantic value. Or you have C-like strings that represent different characters in a string, but the number 0 specifically does not represent the character with the value 0. It represents the end of the string. These are the out-of-band semantics. Or you can have search functions for containers that would find you an object and would give you the index of that object in that container. And again, if you get a non-negative number, you know where the index, where you can find the element. But if you get a negative number, that represents the absence of the object from the container, which is out-of-band semantics. It does not represent, for example, an object that is still in the container. It just so happens to be indexable using a negative index. That would be the in-band semantics. So again, we can make a distinction between languages, but we won't right now. We can only say that if we examine null, for example, let's see how it affects non-virtual method calls. So a language like C# or Java defines that you cannot call a method on a null object. You need to get an exception. So the implementation has to check if the object is null. And if the object is not null, it can call the function, otherwise it needs to throw. Alternatively, what some runtimes do is they call the method, the non-virtual method, they call it as a virtual method, which means access the object's virtual table. And if the object is null, if the object reference was null, then they rely on the memory protection set up by the operating system to trap the access, and then if there's a trap, they wrap it up for the user into a nice exception, and they give the users that. If the access is not trapped, they look up the method in the table and they call it. This is not the end of the world, but it's much less efficient, because now you're calling a non-virtual function as virtual, and you're paying a cost for that. On the other hand, if you choose performance over safety, like C++ does not check for null, then you call the method, and if the object was null, then undefined behavior will be invoked probably sometime later. But if you have Sentinel proofs, if you have null safety, for example, in the language, then calling an object's non-virtual method is as simple as calling a function with that object as an extra argument, and it's just as safe. And this is like a lot of languages are beginning to understand that. For example, later versions of C# actually are starting to become null safe. And this is a very important feature to have. Lifetime proofs is another interesting kind of proof of soundness, because it's actually absent in most languages. So it answers the question of what happens, how can you know that an object is valid, is alive, when we try to use it. And without lifetime proofs, again, languages can choose safety over performance to guard themselves from access to dead objects. So safety over performance here means objects cannot become invalid while the runtime program can access them, and the point of destruction is determined at a runtime cost. There are mainly two strategies for this. One is non-deterministically, by using a tracing garbage collector, like in C# and F# Java Scala, which means basically this is a memory allocator that is, when the memory pressure on the system becomes high, typically stops some or all the threads of the running program, and then inspects all their stacks for global variables, and recursively tracks down more and more reachable objects until it can find no more, and then it destroys all the objects that were not marked as reachable. And there are very sophisticated algorithms and lots of research, interesting research in that area, but this is still an expensive operation no matter which way you cut it. Also non-deterministic. There's also a deterministic way of doing this, using reference counting, which is basically, it involves that keeping a counter alongside an object, and every time you assign that object to a new variable, we increase the counter. Every time the assignment goes away, we decrease the counter, and when the counter reaches 0, we can destroy the object, and we do. There are issues with that, but then again, there's no, it's not free. There's a runtime cost to when it comes to increasing or decreasing a counter. Or you can choose performance over safety, like C and older versions of C++, or older style C++, in which the programmer is given the tools to destroy objects, and it's the programmer's responsibility to infer lifetimes and avoid holding on to dead objects. If the programmer gets that wrong, objects can become invalid while they're still reachable, and when they are accessed, there's usually some kind of undefined behavior that's involved. But when you do have lifetime proofs in the language, then using static analysis, the compiler can prove that a binding is valid, and as soon as the proof stops being true, then the compiler can infer that now the object is to be destroyed. And that does not have any runtime tracking cost. It still has a runtime cost. There's always a runtime cost associated with destroying an object, but not with tracking it in this case. So these are only a few examples of proofs of soundness. There are many more, like you could have purity proofs or state proofs, like RAII, or you can have concurrency proofs and so on. One interesting thing about this subject is that Rust is consistently the safest language in these examples, and in the examples that did not make it in this talk. And yet, even though it's the safest language that we examined, it is roughly on equal footing with C in terms of performance. And it does that by applying the same principle that we discussed over and over. Hang on to as much information as possible and then use it to, one, elide runtime computations to implement language features and to achieve the language semantics. And two, guide optimizations. Use information to make the code as efficient as possible. So we can finally dispel the myth that safety and performance are opposing goals, because all it takes is that missing link. Thank you.
So you had a quote from Eric Lippens about giving up a little safety for a little performance.
Yeah.
So, and he's worked on the C# compiler. Why didn't he bake in the safety into C#?
Well, I suppose that one answer is that Eric Lippert was not from the beginning as a team member of C#. So, he obviously came later with and had to deal with something that we would consider legacy. But it's also, I think, a general rule in software that no software is is built without regrets later. Sometimes, and again, I'm not talking about one specific language here. I'm talking about in general, software sometimes is built towards deadlines and things like that. And if you take one particular example, it's easier to give something that is kind of unsound, provide something that's kind of unsound, but kind of works, instead of waiting to implement a whole features like generics, for example, in a programming language that doesn't have them. So yeah, compromises are, I think, very common in software.
So you seem to imply that some unsafety is inherent in the .NET runtime. If that's so, does it infect what you might consider safer languages like F#?
I'm not sure. Probably not necessarily. For example, yeah, if you have, for example, a way to call a function as a non-virtual, then if your language is null safe, then it can use that method instead. So I would say that probably, depending on the runtime, of course, but probably it's not, it doesn't doom other languages. When it comes, for example, to null safety, when it comes to array covariance, because that's an unsafety inherent in the runtime, then maybe it does. I have not considered that how it interacts with other languages, but yeah.
Okay, not to worry.
It depends on the particular case.
And I wonder how you can prove anything about concurrency.
Concurrency, again, for example, the simplest proof of concurrency being, sound is that if your values are immutable, then safe concurrency comes for free. Or if you have values that are mutable, but they are only immutably shared, that's the model, for example, that Rust uses in order to achieve a language that looks imperative but still gives you the benefits of functional language, is that by tracking how objects are given out as mutably or immutably, then you can, and by knowing what constitutes a race condition, which is that there are at least two actors on an object, and at least one of them modifies the object or the resource more generally, then you can come up with theorems, I guess, for that.
Okay, and maybe a final question, provided the audience doesn't give us some more. So Rust seems like it might be a really nice language to use. But I did try and ask in the chat if people didn't like writing type annotations, and type annotations are often considered noise. I wonder if Rust has type inference like some ML family languages.
Yeah, yes and no. Well, Rust has type inference locally in functions, but not in function signatures, I believe. If you compare it with languages like F# or Camel, I think those would also infer things in signatures. Yeah, there is always a limit to type inference, especially when you're still dealing with concepts like new concepts like lifetimes. I assume they complicate things, but of course I'm not by any means I wouldn't say by any means that I'm knowledgeable on the subject of type inference to answer that very to answer that sufficiently. There are definitely languages that have more powerful type inference, of course, like Haskell is a very obvious example.
All right. Okay. Fantastic. Thank you very much for your time.